All right, welcome. My name's Riley Edwards, and I want to welcome everyone to the William W. Hay Railroad Engineering Seminar Series here at the University of Illinois. Before I introduce our speaker and the topic of our presentation today, I want to take care of a few housekeeping items. If you have a cell phone, please silence it for our seminar. If we have a fire alarm or any other emergency, we'll exit out the doors on either side of the room. We'll go downstairs to the first floor, and then we'll reassemble across the street by the Civil and Environmental Engineering building. Please use the buddy system to make sure we get out safely and get reassembled, so note who is seated next to you. If you did not swipe your ID earlier when you grabbed pizza, please let us know so we can document that you were here. It'll also allow us to make sure that you receive a direct email announcement about our Hay seminars. I would also like to ask Dr. Moreu, our speaker, we may need to repeat questions that are asked in the room so the online audience later on can hear them, so that's another housekeeping item. Now I'll introduce our seminar series in general. The William W. Hay Railroad Engineering Seminar Series is sponsored by the Rail Transportation and Engineering Center here at the University of Illinois, Urbana-Champaign. On behalf of all of us here in RailTech, we'd like to thank the AAR, BNSF, CN, Hanson Professional Services, and the FRA-funded National University Rail Center of Excellence for their ongoing support of RailTech and the University of Illinois. All of us here in RailTech are greatly appreciative of the support. And not only are we appreciative, all the online audience is as well. Today we have more than 200 people signed up online for our seminar, and they reside in 13 different countries in terms of today's attendance. This includes individuals from passenger and freight railroads, transit organizations, federal and state departments of transportation, universities, research organizations, suppliers, and even more organizations than that. And we're very pleased that this many people can join us for today's seminar. If you would like to receive PDHs for your participation, please follow the guidance that was in the email announcing the seminar, or send an email to heyseminar@illinois.edu. Now to introduce today's topic of the seminar. Railways generate large volumes of structural health and track condition data using a variety of sensors and field-deployed instruments. When effectively and efficiently turned into information, these data enable early detection of problems, better maintenance prioritization, and enhanced safety. Today's seminar introduces approaches for improving railroad infrastructure management through real-time sensing, data analytics, and the use of the human-machine interface. Today's speaker will focus on how engineers interact with these data through augmented reality and other human-machine data frameworks. The speaker's research also explores human-in-the-loop methods, including computer vision and robotic inspection, especially to reach hard to identify locations within the track structure. This allows us to form a more responsive model to better prioritize maintenance and improve decision-making. Ultimately, coupling the technologies that our speaker is going to talk about today together allows us to take advantage of the human-machine interface to further enhance the safe transportation of goods and people by rail. So now I'm very excited to introduce today's speaker. Dr. Fernando Moreu is the Robert Stamm Professor of Advanced Design and Construction Practices, the Dean's Excellence Lecturer, and Associate Professor in the Department of Civil, Construction, and Environmental Engineering at the University of New Mexico. Dr. Moreu also holds courtesy appointments in electrical computer engineering, mechanical engineering, and computer science at the University of New Mexico, and is the founder and director of the Smart Management of Infrastructure Laboratory. Dr. Moreu received his MS and PhD degrees in structural engineering from right here at the University of Illinois, Urbana-Champaign. In addition to his academic roles, he's contributed to the design and construction of over 30 railroad bridges in 7 states in the Midwest. His research interests include structural dynamics, structural health monitoring, wireless smart sensors, cyber physical systems, unmanned aerial systems, bridge engineering, and aerospace operations. Professor Moreu's projects have been funded by the Department of Energy, NSF, USDOT, TRB, and the commercial sector. He is a registered professional engineer and fellow of ASCE, along with many other service commitments throughout his career. In addition to these recognitions, we here in CEE and in RailTech hold Dr. Moreu in very high regard, and he's a personal friend of mine. We actually worked together even before I was a student here in RailTech many years ago, and I've learned a lot from him. He's a gifted engineer, and we're really excited to have you here, Fernando, today. You're going to give us a presentation titled smart management of railroads using human-machine interfaces. So welcome.
Thank you, Dr. Edwards, for the introduction. I wanted to thank RailTech and the people in the audience here at Champaign. This was my home for 16 years, and I feel like it's still home for me. Some of the images that you can see here for those in the room and also online are some of the projects that I was lucky to work for 10.5 years as between the master's and the PhD with a company from Urbana, SK Consultants. So some of the motivations of the human interface and in the loop is coming from the job site, where you see important value of the design and the calculations that you do, but you need to actually bring more of a simple ways to share information to maybe increase the safety, have more use of the financial cost of your operations on the field, and I hope it's a topic of interest for everyone. Just to clarify, I'm a civil engineer by training. I got my PhD here in structural engineering, in the civil engineering department in New Mexico. That's my background. The reason I had the appointments is a little interesting. The dean in New Mexico, when I got a student from electrical, was tired of signing forms like, yes, he's electrical engineer, he's a civil engineer, and he called me and said, Fernando, you're gonna get cross-affiliated so you can approve all the program of studies, the qualifying exam, the comprehensive and everything. And then he said, you're gonna do the same the second time with mechanical, you're gonna do the same with computer science. I would say the majority of my students are very open-minded and they like to work with people from different skill sets. They prefer to learn from people who are smarter than them. I am the same. I want to learn from people who are smarter than me. So we work in different areas and we benefit from this multidisciplinary approach. In the railroad, I learned that. So when you work with a complicated system, you cannot be a person who knows about just this area and you teach everybody about what you know. You actually need to listen about experience, maybe new opportunities, new directions that they've been trying, and then we believe that input makes you better. To resonate on the audience today, I think I'm one of those little dots in New Mexico. You're welcome to come and visit. We'll take care of you. We're doing some work with the rail runner there recently, so it's an exciting time for our group, connecting more with the actually passenger train. We're like 5 hours south of Pueblo, Colorado, so many of you in RailTech or the department go to Pueblo, so it's like we just drive there. And we can even teach the class, and at 4 p.m. we jump on the car and we just drive there and check in the little Hampton Inn there. So it's 5 hours for us. For me, for my students, like 4. So obviously, I've been on this seminar many times when I was a student, and it's the first time that I present on the WWA. So I thank the legacy of the department on, trailblazing areas that are more important than ever these days. I was very lucky to know about RailTech, maybe before RailTech existed, with Professor Chris Barkan on the hallway, and because I had that professional exposure to the railroad, to have a professor in railroads was he's very welcoming of conversations. It's not only with me, I know other colleagues of mine, they just stop by his office and they go, how would I say, they couldn't leave the railroad after talking with him. So I know he's online, so we're fortunate to have such a faculty in the civil engineering department like him. It goes without saying, Dr. Riley Edwards is a colleague. We met on the job site in Memphis in the summer, very hot down there. We work with the railroad on the summer, and then we stay in touch. And it's I could say RailTech is in good hands, so I'm very glad to be here, and I'm ready to see what's next. the reputation of the University of Illinois in railroad engineering is unmatchable. And I'm very glad to think that these 20 years I was looking at them, and I've seen it. And I'm very excited to see what the next 20 years bring. It's a very high bar, but I think we're on the right place to go for those things. So the motivation for today goes to this opportunity of working with an industry that really asks you for more. I mean, I experienced that. They don't stop. So when I work as a consultant, they always say, well, can we do a little better? You know, and that makes you better, actually. So here is what I want all of us to think today. Is there a way that we can help the industry to collect data? I know Realtech is very active on this topic to maybe increase the safety that could be enhanced with other ways to collect the data, maybe reduce the time, maybe get more data that typically we haven't collected before and maybe would be interesting to obtain. And this is all in a complex environment, remote environment. It's a place where not easy to access. So I want to talk about some highlights about my idea of this interface and see what you all think. The first one, I had an inspector here using the augmented reality. This is a column that could be a pile, could be timber, it could be concrete, and I need to fill my report for the bridge rating. With augmented reality, I'm not going to use the pen, I'm not going to use any form, I'm not going to use an iPad. I'm going to collect this data on real time, I'm going to anchor the crack width, I'm going to take photos, and they're going to be anchored on that mile post. And then next year, when my colleague comes, they open the report there. Well, on real time, they will get it on the headquarters. The report is being generated. This is the real time in the laboratory. You have the pictures that you just took. And then you can change the report if you don't like it. If you think maybe I should have something of more value to that. Automation of inspection. We recently were awarded with an FRA project for neuromorphic sensing of track. So all of you are familiar with using cameras, LiDAR on the track to collect more data, apply some intelligent algorithms that can be better than people looking at the neuromorphic camera. Is asynchronous data collection that enables you to obtain rare events with a very little latency and only collecting data that is important to you. So we're going to put it on the rail runner, and we're going to be sharing with you how that works. We just like we tried on the indoor. Now we're going to move outdoor. In the last, let's say, 10 years, I've been exploring the robotic help for outdoor applications. One of the topics we talked with colleagues in the railroad, specifically the CM, there is so much that you can learn from your eyes or computer vision. There are sounds that can tell you something. And humans, our ears are not so good for sound, but machines is just data. So it's like the non-destructive evaluation that we are all familiar to do, this wave propagation, and we could collect that remotely. In the topic of vehicle rail interaction, we have our models. We know they are helping us, but there will be non-linearities always that are difficult to collect. We've been working with the Sandia National Lab on this, the traditional frequency content is symmetric. When you increase the force, it becomes like a hardening, eventually an isola. That's kind of the work that I do. Because of time, today I'm going to talk mostly in three other areas that we have time to cover today. The impact on railroad bridges, the displacement monitoring on the field, and the interfaces for some applications on industry. Let's get at that. This is a familiar video for many of you, 11foot8.com. There are a little scary part here where I guess some of you may be the first time. So this is not uncommon because of this. I will just say because of many reasons we keep hitting bottom flanges of railroad bridges down there, and because I can say highways and railroads don't get along too well, doesn't get solved. So This is an example of the solution here. We are trying to provide standards for design a crash beam that can protect this bottom flange. So you can see here there is a crash beam, but we really would like to learn more. Actually, working with CN, George Novak, and so on, say, well, we think it can be a good idea, but why don't you do research about it? And when I went to New Mexico, Sandia National Lab, they like the nonlinear project. And said, oh, that's a great project. Let's do a summer project on this. So that's what we did a little bit, and trying to get some standards on what this crash beam should do to protect the bottom flange of the railroad bridge. So that's what we work on. This is our design. It's a very simple steel component where you have some fuses for the channels connected to the protecting that bottom flange and basically absorb the energy enough to take reduce the energy of the impact, but not, you don't want to be too rigid because then you're going to transfer the energy back to your girder. So it's something of a design problem. This is no crash beam. This is a model. I think Dr. Sagli worked on this. Liu Bi then also on the Sandia project. And that's the flange getting bent. And then this is our approach, a little modeling on this. You see these fuses there? They are not almost filling it. The first crash is taking all that energy there. And then you can optimize it depending on the speed, what are the traffic that you're going to expect, the condition of your through-plate girder, etc. So I was lucky to collaborate with the Earthquake Administration, and we have some large-scale testing of a 1/5 scale bridge. This is a giant knee or a small through-plate girder, depending how you look at it. And this is with the students on the middle of the railroad bridge with a lot of, I think we have 23 cross beams, the knee braces, they just built it for me. That was great. This was in Beijing. And we created a little pendulum. We cannot hit a track inside the lab yet. Maybe someday we'll do. So we have a pendulum calculating the height and the mass, so we get some loss of similitude, and then we can get a similar impact of your top of the highway track into your bridge. Close your ears. That's it, not too bad. So we hit it very bad. We hit many crash beams. This is the plate, then we put the I-beam, and we measure with a lot of sensors. This is a very nice high-speed video. It's like a sheet of paper there. You see that deck plate like bending like nothing after that impact. And this is not like a very, this is a very big beam that it was too rigid. So it transferred all the energy to the through-plate girder, which is not what we wanted. So you see the cable, it's a beautiful bridge there. Actually, I can use this, it's good. And then, I also use the neuromorphic camera, but I don't have here today the neuromorphic. So this is from the bottom up, looking to the bottom flange here, and let's see how it looks. Yeah, that's the track here, hitting on the bottom, and this is the amount of movement that you get. And you're going to have dynamic movement and permanent movement. And the railroad told me, as much as you like dynamics, what we care is the permanent. Because yes, the dynamic is important, but the through-plate girder may be moving a little bit after cumulative impact. So I learned that from them. Again, you can learn a lot if you listen. This is the dynamic movement that for me is amazing. You can get the frequency and everything. But what was interesting for the railroad was to get this offset. Look at the D2 and D4, okay? So the D3, 4, and 1, they're kind of together, and the D2 doesn't really move. So that's telling you, it's going to create a concern on the track, on the next railroad, cumulative a little bit, and you may not see it. You're thinking as a structural engineer on the bottom flange, and they're worried about way more other interesting things that happen. So we did this cumulative displacement, and as you can see, the no crash beam is the winner or the loser, whichever way you want to see it. On the top, this green line, you have a cumulative impact of 10, let's say half an inch after several impacts. And you see how the effective of your crash beam down here is start coming down here. And you get, let's say, like about 50%. This is in the laboratory, of course, of this energy dissipation and reducing this permanent displacement, which is what I wanted to emphasize today. I wanted to switch to the second topic of my presentation. It's about displacement. This is one of the bridges that I work with ESCA in Blufford, Illinois. There's a southbound train of about, let's say, I think it was a 30, 40 mile an hour. And we have the collaboration with the contractor to put a tower and the LVD. So we could measure the acceleration and the displacement. Actually, the railroads were the ones who asked me about displacement. I wanted to use acceleration model, and I said, no, just give us displacement. So again, I learned by listening. You see these columns. This is the red is not good as usual. So this is a Yazoo bridge that was under construction. So working with the CN, they said, if you want a bridge moving, come when we're doing the, the repairs and the construction. So that's what we did. Andy Kimmel, he went there for the summer intern from Railtech. And these are the data that we collected, about close to 2 inches. This is like 10 miles an hour, and this is something that is not, how would I say, the railroad knows that it could be something on displacement that later, when they don't know what's happening, could inform them of something. This is a control environment, but what about that you could have all the displacement out of all your bridges? And then this is actually the Blueford Bridge that I showed earlier, not that much down here, like 7 millimeters. Large disappointment. We thought that bridge was going to move a lot, 7 millimeters for them. Oh, I wanted to move like 1 or 2 inches. So you just learn at collecting more data. So we're thinking is if we could do this collection with cheaper sensors. So that's what I've been doing at the University of New Mexico. You may not remember me, but you will remember LUIS, low-cost, efficient, wireless, intelligent sensors. So that's what you will remember from today. This LUIS is $50. I use it for a lot of maybe education and maybe experimental applications, and they are very accurate. Now we're working on LUIS 6. Let me show you here. And I'm going to give you a sonar LUIS 6 that we can also measure for displacement. It's on, but it's not dangerous. So don't worry, you see a light beeping there. So we like to collect this data on remote locations in a simple variables, like such as displacement, to inform these decisions. This is the result of my LUIS one. So on the Blufford Bridge, this is displacement. The first one is southbound. The northbound is a little more, it's moving a little more, and almost identical. For $50, you can have the same, let's say, same accuracy for civil engineering applications for 300 times less the cost. Imagine you can bring your sensors in your backpack and just, hey, put it on these 5 piles, and we'll take a look for 2 weeks. Or you can take a look immediately. So we're doing that with the Rail Runner now. Take us maybe 10 minutes to install it. We just have it on the online. So big thanks to the Rail Runner.
Thanks a lot, Ryan. We're getting a look at how a UNM professor turned a practical exam into an interactive hands-on learning experience. Well, this was Dr. Fernando Moreu's first time administering this kind of dynamics test, and it was in the Rail Runner. Excuse me now. His previous times were when students applied sensors on the tram riding up the Sandias. Well, this new application allowed students to test critical engineering fundamentals, and it was also in real time on a much larger scale.
The best way to introduce students or people who want to learn about dynamics and not be intimidated with the equations is to actually see the structure vibrating with their own hands.
This class kind of taught us how to deploy sensors, take data, plot the data, all on real time under pressure. So I felt like we were all ready for that exam.
Once students had the practical skills down, there was a normal questionnaire exam on the ride between Albuquerque and Kewah, while the ride back was used to study vibration and movement in a dynamic environment.
Yeah, when you tell the students you're taking the exam on the train, they love you more and more. We recently got a participation on a FRA CRISI grant on short lines. Short lines are very interested in this low-cost approach. It may not be the most accurate if you got 1 millimeter up or down, but it helps you to get some information. Short lines really don't have that many resources, so we want to help them to have same access to data that we are looking is working in the class once we want to try to open that for them. Okay, so we have another video here, and it's going to talk about drones and displacements.
Researchers at UNM have come up with a new high-tech way to move people and cargo more safely. News 13's Francesca Washington explains.
It's not your average drone.
It has 4 sensors on it. The main one is this laser.
Researchers say this drone can keep a train full of people or cargo from going off the tracks, like this train that went off the tracks near Roswell last year, or this one near Artesia. Researchers at UNM want to use this aircraft to improve how railroad companies inspect aging railroad tracks and bridges across the nation.
They're giving us their feedback. Their main concern is safety. They have time and expense problems. So with this, just with my project, after it's done, then there's no need for any of those things.
Civil engineering assistant professor Fernando Moreu says he worked for a railroad company in Chicago for 10 years.
I was working with them on bridges, and I noticed that they were needing some help on their inspections.
He says those inspections are a top priority for railroad companies because faulty bridges can lead to train derailment.
They go and touch the bridge under the train to see if it's moving too much.
So he and PhD student Roya Nesemi have developed algorithms to measure bridge irregularities.
The drone will approach the bridge without the person on it, and you can just wait for your train, collect the measurement maybe in a few minutes, and you are done.
He says the technology is not only safer, but it will also save inspectors time.
With these sensors, we can tell you if it's half an inch, a quarter of an inch, or 1 inch, which is not good.
For now, their research is focused on bridges, but they plan to expand.
We're looking into infrastructure. We're looking not only into trains, we're looking into track, ballast, rock, rail.
Francesca Washington, KRQE News 13.
And the group will present their research to the Transportation Research Board next month in Washington, D.C.
So actually the student working in the project is now a faculty in California State University in East Bay. The idea is that you will have locations where you cannot climb the bridge, or maybe it's not even a possibility. So then the drone could get that access, and the bridge will move on the green, and the drone will measure both the drone movement and the red. So you need to subtract them to get your actual bridge movement. Dr. Nasimi worked on the hardware of the signal processing, but also we were worried a little bit about the vibration. So she did some optimization on the vibration of these carbon fibers. It was a project funded by TRB, Rail Safety Idea, and we also been interested on the collaboration with Los Alamos for this clever interaction with the railroad. I will show you the field, and this is the name of the drone. The Dr. Nasimi named her drone Nasimi, New Aerial System for Intelligent Measure of Infrastructure. And she named the paper with her name. I said, be careful, but the paper was accepted. We used a ground target there. We don't need it anymore with the structure for motion, but this is the validation with the ground laser, about 25 feet tall. And this is the flight with Dr. Nasimi down there. This was when she was a student. And we have some small displacement similar to what would be a timber bridge of a, let's say one of the Yazoo bridge that you saw earlier for that you are interested to measure, but you cannot go and attach the sensor. This is imagine the red line as being your ground truth on the top. These are like 5 cars, okay? And that's the ground truth. This is the real displacement, about, I would say, 20 millimeters, something like that. And then the drone will move the entire hovering with the laser will be between the bridge and the drone moving. So that's, you don't want the drone moving. So you have the camera indicating the location of the drone, which is the blue. And then you can subtract the laser from the camera, and then you have on the bottom plot the estimation on a dashed black line, and the red is still the displacement. As you can see, there is something on the third car. Maybe it was the pilot got a hitch and move a little bit, or maybe the wing made the drone move a little bit, and then your algorithm with the camera is not that good because you get some blurry images on your computer vision. So it was about 20 and 13%, which again, depending on what you're looking for, a few millimeters here and there cannot be the big problem. Masa Sane, she also been working with ESCA. She was interested in contribute to this problem using a Kalman filter fusion between the computer vision and the IMU. Actually, that's something that the reviewers of the paper brought up. And that gives another use for Lewis with another sensor, which is what the students like, create something that hasn't been done before. And we combine the position of the drone, increase accuracy, because regardless of how good the camera is, you're always going to have some inability of locating the movement of the drone. So the IMU with the camera can be a good alternative. We have the prediction of the position. We work also with Piedad Miranda. She's mechatronics background. We add an update of the estimate, and then we correct with the displacement. Flying is a little stressful for research. I crashed many drones. I won't tell you how many or where. So in the last 3 years, we got an Hexapod. This is a good tool for replicating hovering on the lab without crashing. And we can use it also for, actually the Navy uses it a lot for the boats, right? So we use it for the drone. In this case, Piedad Miranda and Michael Carl have been working on this. And we've been collecting some, this is a little secret, 200 people is not what I thought. We fly inside the building, but he's licensed, so we are okay. And we collect the hovering with the Vicon camera. And that way we can experts on drone hovering, which is interesting, because I thought a lot of people would do this, but people I guess, don't know the potential of learning this position for bridge displacement. So that's why we're doing it. And this is the setup. This is your, let's say your railroad timber bridge. This is your ground truth. You're gonna have a little laser on the drone, but we need the ground truth on the lab. So this is the $80,000 Polytech laser, the one that we bring to the site. We collect some of the movement with the Hexapod, with the Vicon camera, so we'll see how it hovers out there. It could be wind, it could be when you get closer to the rain operations, you may not be able to keep the drone ever still. And with this information, we do our experiments. This is Masa, Piedad, and Michael. This is a little hovering. As you can see here, we have two lights. One is the green, and the other one is the red. The laser is the red. That's the actual laser measuring displacements. When we fly out there, you don't see the red. I mean, I'll give you $100 if you say. So we went to, this is another secret. We bought the laser rangefinder for hunting, and the green one is the one that you see. So that's how you know where you want the drone to fly. And we got a little better results, but let me show you just the table so we can go to the last topic. Masa created 4 scenarios, like only transverse, pitch, yaw, raw, with certain degrees that she got from the original flight on the drone. The red is the original algorithm. The blue is her updated extended Kalman filter algorithm. The average is evidence of the improvement of the displacement. For the last topic, I want to repeat this message about that I hear from the railroads. They understand the data is helping already. They've been using it for 100 years. But if we could bring this automation of sharing information, this exercise was done by one of the high schoolers. I hire high schoolers on the summer. Maybe that's another secret. We can do that in New Mexico. So they get a little salary. They get to work with graduate students. And this is a high schooler, Sho Komiyama. He did this. And then he gets excited about railroads. So the crash beam that I did earlier with Xinxin Yuan, she's Dr. Yuan. Now she's in Minneapolis. This is when I met her in Beijing. So this is the interface with the crash beam. How could I collect? Actually, the railroad mentioned that to me. I just want to go there, look at the beam, and tell me how much it moved. Say, okay, because otherwise I need to stop the traffic, stop the highway traffic. I don't like the highway traffic people. I just want to look at it and see how much it moved. So with that inspiration, we can collect on real time the 3D deformation. You could even integrate the volume change after an impact, not just the displacement. Remember, how many cubic inches have we lost on this impact? Another thing that I learned with the railroad, I need to go to the Cairo Bridge and get on the forklift and wait there, and then you need to go with the harness and everything. You need your hands. With the HoloLens, we envision an opportunity for increasing the safety where there need to be carrying. I think if I have an iPhone then, I would have lost it on the Mississippi a lot of times, Ohio River. So this hands-free gives a lot of power for the railroad. You need them to be up there safely. You don't want to bring a lot of gadgets with you. So applications that we have, examples. This was actually Martira Mullen from CN now in Amtrak. She said, well, this is information with structures is great. I just want to see the rail gauge, you know. We need to go there. We need to measure the rail gauge all the time. If I don't have to bend, you know, if I don't have to, still have to do it as a human, but if I can automatically, eventually, we could include this. So you are collecting the data, but even this may be as accurate as you could do with your hands. And you could be there, but you don't need to be collecting all things manually. We test this on the Chorus Lab company there in Albuquerque. I'm interested in the human factors when I hear for inspections with the CIA and Sandro mentioned, well, it's so, I mean, you do an audit and you see if the inspections stay the same or they change. So that's how you check the inspection quality. So I'm thinking, what about if I audit myself? So I will put the HoloLens, I collect the eye tracking, and I see where I look during my inspection. The purple line is where my eyes move on the inspection. And I can know when I look on the entire surface that I was supposed to look for. And I can say I did a good coverage of the concrete beam that I had to look at. Of course, this brings a lot of psychology experts. We're writing a proposal now for the eye tracking with a psychology professor in Las Cruces, New Mexico. And I've been working in this topic maybe for 5 years. We got 2 projects. One was with the TRB rail safety. They're very interested. And the other one was the BAA from the FRA, human factors in the SCAR. And I think it's a good idea from the railroad to bring this objective information to the railroader so they can learn how to learn faster. Why wait 2 years to learn your job if you can accelerate the learning with augmented reality? This is work on the crack detection for concrete. We work again in this interest for quantifying automatically so we can track them, keep them on the location. I was talking with Professor Popovic earlier. There is a lot of knowledge that we have on the rail. Recently, there was a derailment in Spain in the high-speed rail. It's a rail problem. So there is a lot of opportunity to make this center more important than ever. There is a lot of information that we can automatize and bring. The railroads are interested on your work. So this is the automatic crack detection on concrete on this case, and we have accuracy of about 0.2 millimeters, which is good enough for concrete. I understand for steel, you will be dealing with other measurements. But remember, you can marry this augmented reality with any sensing technology that you have. We're working on the interface part. This was also from Dr. Yuan there. And this is, I will skip this part. It's more like the secret of the augmented reality. On the early years, the Los Alamos lab could not buy an augmented reality headset and have it running on the hallway because they don't like that kind of thing. So they donated one to the foundation of UNM, Dr. Mascarena, so I could get it. I can do anything I want, I think, with the HoloLens running around. And we did some kind of investigation. The secret is for computer vision, you need to convert your 2D matrix to very long 1D. You can send it with your socket to the headset, and then you can reconvert it back to your matrix. That's the secret. It took us like a lot of fights there. The second secret is for the automatic calibration. With AI, obviously, you do your training, and I know I'm still involved with a PhD thesis so in the department. So I know this is a very active topic. You guys are publishing good work. But the calibration part is, we need to have let me go back here and run it again. You see a little blue box? The blue box is projected in your pixels. You have the distance and the angle of your headset to the wall. And you can calibrate automatically because you know the dimension of that rectangle. So then you can convert the pixel to the width of your crack. We did a workshop with the bridge inspectors in New Mexico, and they said, I don't know how accurate is your algorithm, but I need to be able to walk and move around my neck, and I should be able to look up and right or left. I cannot be 2 feet, 0 degrees from the wall. I cannot ask my inspectors to do that. Bridges are not where you want them to be. So we changed that, and we had these are some of the results. You see a 0.22 millimeter. That's very, very good for concrete cracks. And again, it's about 0.7 seconds delays, almost, I would say, good enough for humans. You could make it a little faster, but it's a very, very real as you are looking to this data. I was fortunate to test this on real scale structures. So I got a Fulbright in 23, and I went to the National Taiwan University, NTU, and we worked there with I could present this to the high-speed rail in Taiwan. And we're interested in seeing how can we together bring the great opportunities that we have with this data and automation and think about the future. Maybe, prepare for the 10, 20 years. How are these tools which tools of these are the most useful for them now? The last part of my talk, and it's, again, we are getting new interest on robots and railroads, maybe for safety. There are many things that we believe automation could enable us to collect data more safely. This is one of the applications. This is Dr. Khorasani collecting the crack width without AR and with AR. More accuracy, you could argue. You could also say it's going to permanent record on that inspection. So you could be your culvert, it could be your retaining wall, it could be your pre-stressed beam. You could have it permanently anchored. This is a little work on the robotic helping on these repairs. Actually, I'm becoming interested in welding. I'm not a welder. I wish I would have done that before. I work with welders, great people. So there are a lot of opportunities for welding where it could be some of the weldings we can automatize them. In repairs, it could be that these inspections, instead of going back home, actually Chuck Farrar from Los Alamos National Lab mentioned on the PhD defense, why don't you repair as you see the crack? I said, wow, that's a very simple idea. Yeah, that'd be great. So robots could be doing that for some of the cracks, okay? For some of the repairs that are more in a category that you should be doing there and check them off and take care of the difficult ones. And this is Ronan. He's one of the high schoolers that have been with me for 4 years. Now he's junior in UNM. If you work with the robot, there are some concerns. You may bring unsafe environments between the human and the robot you didn't have before. You can trust, to a certain extent, some people and the robots, you don't know what they're up to. So we've been working on this opportunity for advance this collaboration with robots, helping the railroader on real time. Dr. Malek, he developed this rapid experiment random tree star for human, let's say, repair collaboration. Maybe a start point is the red point, and I want to go from point A to B. If I have an emergency, like Dr. Edward was saying, we were told what to do, but we're not machines. We may not even follow his advice. We may be thinking, which door should I pick my phone? Machines are better. You tell them what to do, they just optimize the path. So for emergencies, for trajectories, maybe it would be better that the machine tells me these are the 3 paths that are okay for you to take, choose the one. And then based on my experience, Dr. Peck say, engineering judgment, I can pick one of the 3, but I don't need to do the optimization myself. Hector Valenzuela, he's a PhD in electrical on our group. He's been working with this concept, and these are some of the, maybe I will go to the application here, some of the applications here. So you have a mixed reality between your robot is following, the robot has rules. Actually, robots don't do whatever they want. Believe it or not, they don't think. So you have your model, and you optimize it to do certain things. The robot follows the model. You want the model to be optimized for some activity, but the robot is not following you. The robot is following the model. So what we created, or CAVE created, is this interface with 3 realities. You will have the human wearing a HoloLens. You will have the robot reading the model that you want them to do, and the human will be looking to the, let's say, interface with the positioning of the robot. The augmented reality captures the position of the hand gesture with that coordinate and bring it to the model up here. The human believes with their hands that the robot is following their hand. And it can even change the optimization with the human. It could be empathy, it could be safety, it could be, this is something happening here that we didn't expect to happen, stop. And the robot will see the human gesture on the augmented reality and stop. So you have really 3 words like one. Looking at the path brings safety to the humans. Now you can train humans with robots. So in this case, we have a very simple trajectory, A to B, where you want to obtain a smooth path. And in this case, you have the no obstacle, and the human will want the robot to do it for them. So once you send it, the human is free, doesn't need to control the robot, because I know what the robot is up to. I like working with this robot. I know what they're going to do. No surprise for me, no accident. Now, it could be that myself, my colleague, or another robot interfere with that path, the path of the robot, the program path of the robot. I will have the RRT start to recalculate this new path for a optimization purpose. The robot is going to be faster than me. I don't want to recalculate what to do. I just approve it, and the robot goes safely. And again, the robot is using robotic superiority, and the human is choosing what to do. Going back to the multiple path, CAVE had to make it a little more difficult. So we're going to have multiple obstacles, and instead of giving you 1 RRT star, I'm going to give you 5. And you as a human, again, you will just see the 5 and choose the one you like. So he put these obstacles on the path just for you to observe. We will have 5 possible paths here. And then you, as a human, decide to go with the shortest path, maybe for energy, or maybe because far away from humans, and you know, everything being equal, you wanted to do it on the back. And then the robot just goes there and conduct the activity that you wanted them to do. A lot of opportunities to increase safety with some automation that today is becoming more possible than before, and we can explore them together and see what could help to make these decisions. And that, as you see, the robot is conducting their tasks without interfering with these obstacles. Great, so I have the future here. Last video.
Of engineering took middle and high school students on a unique trip to teach them about STEM. In June, the department took 26 students on the Rail Runner to conduct an experiment using a motion sensor. The students collected data on the train ride that could be used in future management decisions. The study, which was part of a larger 3-year project, aimed to interest more New Mexico students in STEM and to give them practical experience. It was created through a partnership with UNM and the Federal Railway Administration.
So we are very excited to create this environment of innovation in New Mexico. We have 3 national laboratories. We have a lot of trains there. We are trying to recruit more people for the railroad industry. Once you start very early, that was a project with FRA. They just believe they will be railroaders being smart with operations. Safety is important. They get it. There is a lot of careers that we are just unfolding. And as you see, we start very early. These are like 6, 7, 8-year-old, and they just love the railroad from now on. This is one of the workshops we did there. I think it was 110 people. We have little people here. Even, I think we have like a 2 or 3-year-old there. But, you know, we have families, actually. These are a lot of homeschooling in New Mexico. And the parents said, this is all great, but give me something simple that I can, you know, reinforce at home. So we just teach the parents now, not just even the children. If the parents love the railroads, the kids will love the railroad. And this is the poster that Masa put together. These are some of the people on my team that help here. And this is one of the high schoolers having a good time there. And this is the sensor class. You see, this is maybe 70 people there teaching the class, and they're getting ready for the train. So in conclusion, and I'll be very interested to see the interaction with people, the future railroader will be able to see on the field, on real time, share data, optimize things more asynchronous, multiple locations, multiple time, near real-time decisions to assist railroads to make informed decisions at the job site. And they're interested in this opportunity. So let's see what we can do on that direction. New opportunities to continue building this technology center, Rail Tech Center. Is just congratulations on what you're doing, and can't wait to see what the next 20 years do. Thank you for your time.
That was excellent. Thank you very much. We have time for questions now. So, how about anyone in the room have questions? We'll use the mic.
Well, it's interesting that you started out with the side hits on bridges, because about 3.5 blocks from my house is a low bridge. It gets hits all the time.
Oh wow! Congratulations.
It's about a 36 to 40 foot through girder bridge, double track, but there's only one track on it now. The problem with that is it's not so much that they try to shield it, is that whatever gets hit, depending on what hits it, it just knocks it sideways off the bearings. So knocks the track out of alignment, and the police call the railroad, and they come out with a couple of trucks and jacks and stuff, put it back on. So it would be something, you couldn't really mount anything on the side of it that would help that. You'd have to probably mount some kind of a framework before the bridge on each side for the truck to hit rather than hit the bridge itself.
Great. So the comment was that maybe you can do something before you hit the railroad bridge. The comment that I have, we thought about it, and there is a little problem with that. If you build a new structure and put it, let's say, 100 feet before, you're liable for something that you bring to the game. The railroads don't like that. So you can do a little thing, but you cannot do too many things, because the one who pays is the one with the big pocket, and the railroad always lose on that conversation. The bearings, you bring a good point. The bearings is a very good area to look into for this, these lateral impacts. And again, it's an active problem. It's interesting that we still have so many of these. So thank you for the question.
More questions in the room? I have one question for you, Fernando, in this. You covered a lot of different topics that you're working on, and one of the challenges we often run into here regarding data is when we want to think about change detection, run over run, or inspection over inspection. I know you showed the Yazoo Bridge and it being monitored 3 times. That would be easy enough to replicate, and your repeatability is high. What about some of the other types of data acquisition that you talked about? How do you do alignment from inspection to inspection? What's that?
So that's like Lagrangian problem. So you have, temporal data and distributed data. And I mean, people in GIS, environmental, the river, they're dealing with this. But I think for us, I'm interested on this neuromorphic anchoring, where you can synchronize across time and space with that's the camera on the vehicle, because that was a BAA actually, what you just described. So it's a real problem. It's a real opportunity where you need to actually anchor these data collection systems with the mileposts and be more automatically anchored, because otherwise it's too much to do. So I think it's of interest for the FRA. So.
Good. So a question from the online audience about your comments on drone inspection. What method do you use to calibrate the camera parameters and reconstruct the displacements that you obtain?
Should I repeat the question?
It should be okay.
So on the laser is the only one measuring the displacement. The laser is between the drone, the laser is attached to the drone. You shoot to the bore or to the timber bridge, and the laser measures the displacement. The camera is filming the position of the drone. And we just did a pinhole camera for assuming only X and Y location. And you just measure the X and Y location of the drone. Yes, you can obtain the other 4, the rotation, but it gives you some problem because of the camera resolution. So we added the IMU to get the IMU on the drone, and then you can get, again, the position of the drone, not so much the displacement. The displacement needs to be with the laser. The dynamic displacement is only collected with the laser. The camera and the IMU is the position or the trajectory of the drone. I hope that was clear.
A couple more questions related to drones and bridge displacement measurements here. How could transverse displacement data be further used to assess the condition of a bridge?
A great question. We are working now with the rail runner. They have let's say, a small amount of bridges. I think the CM may have thousands, and BNSF. This is like maybe a handful of bridges. Let's say 40 or 50 bridges. They do their inspections. They work with Herzog. They have their. These are, timber bridges. They've been there maybe close to 100 years. In addition to the inspections and the decisions that you will do based on your territory or your bridge inspector, the displacement will be another information that you may or may not use to confirm or explore another bridge that you thought was the one that was the best. If you see that bridge moving a little more, we're talking about 6 millimeters instead of 2 millimeters. If you find that 6 millimeters, that's an additional source of information for that. Maybe send someone there and look. The sensors are there. We look at the data remotely. So you could have this displacement-based, alert to send someone there.
Okay. One more question about drone inspection. If the drone is operating under the bridge, is it effective in capturing measurements up under the bridge in some of these larger structures? Can you talk about that?
So they're worried about maybe the crashing the drone or the
accessibility and some of the
yeah.
Getting up under some of the girders.
Yeah, so that I was talking with the head on the industrial systems. There is an interest of the drone perching on the bridge, for example. You don't want to be going through all the race crossing. And these large bridges, it's a little difficult to go through them. So you could perch your drone there. I think there is also an opportunity to have like a swarm of drones. So you may get more value measuring with 5 drones a little farther than one drone on, getting closer. So there are optimization and control people that likes this problem about, complex environments.
Any questions in the room? There are none. How about a round of applause for Dr. Moreu? Very small token of our appreciation from Railtech here. Your name, your photo should be somewhere on here if you look closely.
Okay.
But we're grateful that you were here. Thank you again for coming and giving an excellent seminar. So,
thank you.
And we'll see everyone back here in 2 weeks. We'll have another HAY seminar and several more planned after that for the remainder of the semester. So more details on our next seminar will be coming out soon. Have a good day.